Hello, my name is Paul John Balderston, and today I'm going to be talking to you about black holes, gravitational waves, and how we detect such high-energy, violent phenomena. You see, black holes and gravitational waves are theoretical predictions of Einstein's theory of general relativity, which tells us that space and time itself, the very fabric of reality, is not this rigid, unmoving thing that we just walk through and have our clocks tick by. It is a dynamic geometry, a field that bends and curves and twists and responds to how matter, something like us, a star, moves through it. Granted, we don't distort space-time very much, but we see very large amounts of this curving of the geometry around stars, which is what pulls planets into them. Really, you need a lot of mass to get a lot of curvature. Sometimes, if you get enough mass in a small enough region of space, you'll start to get an infinite amount of curvature to the point where you then form what is known as a black hole, a region of space where it's so highly curved because you've had such a massive object, such as a dying star, fall into a point where it can no longer get out. Not even light can escape from the black hole. These are the most massive regions of space because they contain super compact, dense objects. And we said, mass distorts space. Now, black holes can still move through the universe as a star would move through the universe and rotate and spin and such and so forth. And sometimes two black holes get close enough together that they then start to affect themselves gravitationally in a very, very strong manner, and they coalesce and spiral together until they eventually collapse together. And such high-energy events send out ripples in the fabric of space-time itself through the universe, till we eventually get to our little blue planet here, the planet Earth. And this stretching and squeezing, this ripple in the fabric of reality, can be detected by the LIGO experiment, these gravitational wave interferometers that measure the stretching and squeezing of space by getting a laser beam in a long 4-kilometer tunnel, two tunnels orthogonal to each other, to measure the stretch of one and the squeeze of the other. When a wave passes through, this light takes a little bit longer and a little bit shorter in one of the other tunnels to travel from one end to the other and back to the source. And the scientists measure the stretching and squeezing of this tunnel, which is only about the width of 1,000th of the nucleus of an atom. Incredibly small effect, but incredibly sensitive detectors. And this has provided another proof that Einstein's theory is correct, that black holes do merge, and has opened up an entire new avenue for seeing things that we would have never been able to detect. No light comes from black holes. We would have never been able to take a picture of the black hole itself, only stuff going into the black holes, and we can now study the structure of the cosmos and its fundamental geometry in a way unlike ever before.